We have moved in some respect in the 1900s, in the 20s, and now the 21st century into the realm of modern physics, which in some respect is just an extension of the classical physics. In some respect, it's a shift in the way you think about the world. I'd like to spend some time in this last lecture looking at a little bit at some of the key developments of modern physics. Just an overview so that we can compare and contrast the difference between the modern physics and the classical physics. It might help us to understand the usefulness and the power of the classical physics as it still continues today by seeing what is different about modern physics. For instance, Albert Einstein is really the hero of modern physics, and Albert Einstein was in many respects throughout his life very much a classical physicist. He looked at these old ideas, respected them, and in many cases believed them so strongly that he was able to build them further. Yes. One of his earliest examples was the theory of special relativity. Now you might think that the whole new branch of physics that has nothing to do with classical physics, but on the contrary, it was really developed by Galileo. Galileo invented a relativity, or at least he is one of the inventors of relativity. We talked about this. Galileo argued that there are laws of nature out there and we are learning about them. Those laws of nature are, to a certain extent, independent of the human and who is observing them. This was very big and important idea in the classical physics. It said that I can observe an experiment and you, an independent observer, can be moving past me with a constant speed and straight line. We are in different reference frame. We make measurements. We disagree on many things. Speed is relative, velocity is relative, position is relative to the observer, but the law of physics are invariant. They are the same. We both agree that F equal ma. Sure. Albert Einstein thought about this, and he believed it. He understood that this was a statement and profound statement about the nature of the world we live in. He didn't change the idea. He also looked at the Maxwell equation and said these classical ideas are very deep and very profound, and they seem to be matching experiments so well that they seem to be telling us something true about the world we live in. Now, if you combine Maxwell's equation with Galileo's principle of the relativity, you discover something very interesting and very radical at that time. Maxwell's equation tells us that the speed of light is a constant, independent of the observer. Wow! The speed of light is itself a law of nature. You might just accept that as a fact, but you have to think about it. It's weird. I just said speed is relative to the observer. Imagine that you are running away from me at very, very high speeds. You are running away from me at 3/4 the speed of the light. And I shine the flashlight beam in your direction. I measure the speed of the light that beam to be the speed of the light 100 million meters per second. You are running away from a flashlight and you turn around and you do some experiment to measure the speed of light that beam. What do you have? If you are simple and classical, then you would have reduced the speed. You would have reduced speed. If you are running away from the thrown ball and you measure its speed, it seems to be approaching you more slowly. You measure its speed to be reduced. But not light. Light is different. It's a law of nature which Einstein recognized that the speed of light is the same to all observers. What? Yes. Now, that's difficult to make sense of, and ultimately, in order to make sense of it, Einstein realized it's not relativity that's wrong. It's not Maxwell's equations that are wrong. It's our kind of intuitive understanding of space and time that needs to be revisited. Wow! Newton believed that the space and time were rigid, fixed, universal, and completely independent of the observer. It was a natural belief. It forms a core idea in the classical physics, and that was what Albert Einstein realized needed to be tightened up. We need to make operational definitions obeying the philosophy of the classical physics in the practice by trying to define precisely in the laboratory what we mean by time and time intervals. Once you do that, you realize that a certain aspect of the Newton's law have to be fixed. We have to rethink our definition of time and space, which we barely thought about in this course because we just accepted them as our underpinning core principles. Modern physics simply questions the definition of those underpinning, and so it doesn't eliminate Newton's law. Sure. They are still quite correct. It's just asking a question about where they come from and what the core of classical physics is itself. If you think about relativity, it changes some of your ideas about space and time. It requires that you redefine the momentum. It's not just a mv anymore. It's just an mv, mass times velocity anymore. You have to fix up the formula. Now, does that make Newton wrong? No, not at all. When you fix up the formula, you still have effectively mass times velocity. You still absolutely have a conservation of the momentum. It's just that when the objects are going at the extreme speed near the speed of light, you need to make subtle change in the way you think about what momentum means and what kinetic energy means. It is very important if you are worrying about objects that are traveling near 300 million meters per second, which has essentially no bearing on anything in our ordinary lives. It's nice to know about it, and it's a shift in your philosophical underpinnings. Yes. Einstein's theory of general relativity did a similar thing. Remember, Isaac Newton has written down the fundamental law of gravity, and we talked about it and understood how useful it is. Einstein didn't throw that away. He again asked where it comes from. How do I make sense of the gravity itself? In classical physics, we just sort of shrug our shoulders and say, it is what it is. It's a force that attracts the Earth to the Sun. Once we accept that we are off and running, we describe the planets and the tides and the eclipse and on and on. Everything you can think of, even rockets to Mars. Albert Einstein says, yes, that's all great. I'm not going to throw that away, but what I would like to know is why. Yeah, me too. Takayuki too. Why is there gravity? It's a delicious question. Yes. In the old days, it might have been a philosophical question, and Albert Einstein turned it into a measurable question. The general theory of the relativity now reimagines space and time in a geometrical sense and let us have this new idea of what gravity really is and where it comes from. It's fun to learn about, and I encourage you, after having studied classical physics, to study some more physics and learn about the underpinnings. One of the directions in which you might go, if you push on in classical physics, is to say, okay, we started classical physics at its core with atoms. We postulated that started classical physics. We postulated that they exist. They are real. They are out there in the world. And once we believe in them, we can understand the colors of objects, right? The texture of objects and the behavior of objects. Thermodynamics and heat engines, all of that. None of that goes away when you ask a question, what is atom made of? It's just delving deeper. You are asking, okay, what is that atom? How do we understand it? When we investigate that, it is a field of quantum physics which began around 1900. That's why I set 1900 as a shifting point. Whoa! Yes, it was when we began to ask some new and different questions. Yes, this is what I all need to do. After mastering classical physics. Quantum mechanics asks about electrons inside the atoms, and here again we discover that Newton's laws are insufficient. They are inadequate to go down to distance scale of billion of meter or smaller. When you start investigating the subatomic structure, you discover to your surprise that not only do Newtonian laws needed to be fixed, and those are the law of quantum mechanics. So Newton's laws are classical mechanics. But you reformulate the law of physics and also begin to ask questions about the assumptions that we have been making, such as determinism. Yes. Yoi. In the classical physics, it is taken essentially a philosophical article of the faith that if you know enough about the world today, you can make a quantitative prediction about the world tomorrow. Now, classical physics recognizes that sometimes it may be complicated, as with weather. Nevertheless, it is a belief that we can predict the weather. We do pretty good job certainly for tomorrow or even 2 or 3 days down the pike, which is better than we used to do. You can easily imagine that 20 years from now we will have this even better long-range forecast. But if you are looking at a subatomic particle, such as a radioactive nucleus, and we understand that radioactive nuclei decay, and you ask when will it decay and what is going to happen in the future, it's interesting. Quantum mechanics says we don't know, and it's not that it's just difficult to calculate or it's complicated. It's that nature itself doesn't know. Whoa. It's not determined today when precisely that nucleus will decay. It's a wild idea, and it turns out we can describe nuclear decay very, very accurately on average. I can tell you, if I have a million of them, how many will be left tomorrow and a million years from now. But I can't tell you specifically which ones. It's like an insurance company that can tell you very, very accurately what human life spans are when people are married and so on, but they can't tell you about you. Quantum mechanics has shifted a little bit the way we think about this fundamental philosophical point. Maybe the world isn't fully deterministic. Sure. Now again, you can ask the question, does learning that in the early 90s threw away all of these wonderful ideas of the classical physics? My viewpoint is that it's not even remotely the case. Classical physics describes the world we live in as accurately today as it did in the 1600s when Isaac Newton was first making sense of it. Again, it's the underpinning down at these levels that are far, far beyond our ordinary experiences, and it's useful to know about it. It opens up new branches of physics when you start asking these questions. Classical physics will not explain or predict a laser beam. A laser beam really arises from the quantum mechanics of the electron inside of an atom. On the other hand, classical physics does a perfect job of explaining how that laser beam behaves. Yes, it behaves just as Isaac Newton thought. It goes through the lenses, it focuses, we understand the color, we understand how to build a CD player with a laser beam, or there's a scanner at the grocery store with the laser beams, because ultimately the microscopic phenomenon of the laser light is just classical physics again. It is predictable and understandable. It is only when you ask that deep question of the where did it come from that you might need to and want something new. In this respect, modern physics has built on the classical physics. It doesn't throw it away, it enriches it. It starts to take that framework, that the cathedral, and it now builds something underneath it. Some even deeper layers still. We may not be done. Classical physics continue to describe aspects of the practical world. Quantum mechanics continue to be studied and deepened. It's not necessarily clear that there is an end point. Classical physics has led us to believe that science is an investigative process. We are trying to make sense of the world that we live in. It is absolutely, in my opinion, the most fruitful, powerful, and productive discovery of the idea in the history of human civilization. It has had an enormous impact on the world that we live in, the technological world that we live in, and all of the aspects of our lives are built upon and centered on the classical physics. Yes! We studied it not because we are interested in history, but because it really is telling us something very useful about the world that we live in and the things that go on around us. If you want to understand how a baseball behaves in a baseball stadium, or how the electricity for your house is generated, or how your microwave oven works, these are ideas that can be understood from the classical physics. Sure. Yes. It's a truth. If you leave this course and all of a sudden you realize that there are some important political issues involving energy and the environment, you should recognize that the tools of this course are sufficient for you to understand the scientific questions. Now, that's only one piece of the story. You have to think about the politics and the ethical issues involved in, and classical physics may or may not be helpful for you to move in those directions. It is enormously helpful for you to be able to separate science from the wishful thinking as well inaccurate thinking. If you are thinking about limitation in addition to the environmental consequences, energies, conservation of energy, and the definition of power and its relationship to the energy, it's very, very fruitful. My hope is that by the end of this course, the energy you put into it has changed a little bit the way you think about the experiences that you have. Go out and think again when you are driving your car, when you are at working, when you are riding your bicycle, when you are looking at toys, when you are just thinking about the world around you. I hope that this inspires you to continue learning. There is an awful lot more that you can continue to study in the field of the classical physics alone, and I think it's wonderful when people make the effort to make sense of the world they live in. Thank you very much, Professor Stephen Pollock. See you the next lecture.